afternoon, everyone. My name is Xintong Li. I'm from Shenyang Aerospace University of China. It is a great honor to share my paper with you here. The title of my paper is Image Encryption Algorithm of Cal System Adding Cosine Exciting Function. I will introduce my paper from three aspects. They are background, research, and experiment. The first is the background of the research. Text data encryption technology is relatively mature, but these algorithms are not suitable for image encryption. There are two reasons. The first is the image data is usually presented in the form of a two-dimensional matrix, which is not suitable for one-dimensional text encryption technology. The second is the image contains a large amount of data. Its adjacent pixels have high correlation, and it has high redundancy. On this basis, people propose to use Celtic system to encrypt images. Celtic system is favored by its uncertainty, unpredictability, and non-repeatability. Celtic system can be roughly divided into low-dimensional Celtic systems and high-dimensional Celtic systems. Among them, the low-dimensional Celtic systems include one-dimensional Celtic systems like logistic mapping and sign mapping. Two-dimensional Celtic systems have timed mapping. High-dimensional Celtic systems refer to Celtic systems with three or more dimensions, such as the Lorentz equation. In the paper shared today, an algorithm for image encryption using a Celtic system is proposed. First, I will introduce the construction of the Celtic systems. Sprott summarized some Celtic systems in 1994. The mathematical model of a system is the formula on the left. Adding the cosine excitation function to the X controller can get the equation on the right. Next is the Lyapunov exponent spectrum of the improved A system when A equals 5, B equals 2, C equals 1, D equals 10, E equals 15, R equals -1, and omega equals 1. The Lyapunov exponents can be used to analyze the characteristics of Celtic systems. As you can see from the graph, one of the exponents is always greater than 0. It shows that the Celtic system at this time is in a Celtic state. The following picture shows the Celtic trajectory of the system starting from 111. It can be seen from the figure that the trajectory of the system doesn't exhibit regular motion, so the system is Celtic. The following is the value range of A, B, C, D when X changes. It can be seen that the parameters have a large range. The balance point will affect the stability of the system. The following is the calculation system whether there is a balance point. First, let the R cosine omega t equals n and independent of X, Y, and Z as the second formula. Second, let the right-hand side of the equation be 0 as the third formula. Next, solving the third formula to get the system balance point is 0 square root of D divided by E. And then we can get the Jacobian matrix at the balance point as the formula on the left below. After that, we will get the eigen matrix of system as another formula. Let the system characteristic matrix equals 0. Finally, we can get the eigen values as follows. All eigen values have non-positive real parts. According to the Lyapunov stability method, the system is symptotically stable at the balance point. Next.
Is it just me that doesn't hear? Are there some issues?
Yep, I think she's not audible. Miss Lee?
Okay.
Miss Lee, you're not audible.
This is the bad part about giving a presentation, then you don't see if there's someone trying to speak, especially if the connection is bad.
Yep.
Okay.
Miss Lee dropped out again. Let's hope that she gets back.
Hello, everybody. Can you hear me?
Yep, we can hear you now.
Yeah.
Oh, okay. Let's continue.
Yep. Can you start from slide 8, please, if you don't mind?
Okay. Let's start from this picture. This picture is the flow chart of the algorithm. First reading the plain image and then obtain the initial value of the chaotic system through the hash function, performing a series of processing on the sequence generated by the chaotic system. Encryption algorithms based on chaotic systems are generally composed of two methods, permutation and diffusion. In the paper, the image is scrambled by zigzag transformation and line displacement. Finally, the diffusion algorithm is performed on the image. That is the whole process of the encryption. Next, we first introduce the zigzag transformation. The picture on the left is the transformation method of the original zigzag, starting from the upper left corner, traversing the matrix in the order shown in the figure, and put the elements sequentially into a one-dimensional matrix. The transformation is completed by reshaping the one-dimensional matrix into a two-dimensional matrix. It is obvious that no matter how many times the transformation is repeated, the positions of the first two digits and the last two digits of the matrix have not changed. It may leave an opportunity for the attackers. And therefore, we change the starting position of the zigzag to be the lower right corner to make the positions of all elements in the matrix vary as much as possible. Row shifting after zigzag can be described as the first row of the image does not move, and starting from the second row, the elements of each row are shifted to the right by I subtract 1 bit, where I is the number of the rows. The last is the diffusion operation. The execution order of the proposed diffusion encryption algorithm is first dividing the matrix into two equal length one-dimensional matrices P1 and P2. Secondly, XOR P1 and the chaotic sequence X1. Thirdly, adding P2 and the chaotic sequence X2. Next, add the results of the step 2 and step 3, and then XOR the result of step 2 and the chaotic sequence X3. Finally, contacting the results of the step 3 and step 4 to obtain a one-dimensional matrix with the lines of m multiply n, and then reshapes it into a two-dimensional matrix to obtain the cipher image. At this point, the encryption process is over. We choose 3 images of Lina, Baboon, and Pepper to be tested. Their respective cipher image and are shown in the figure. The security and the feasibility of the algorithm are verified by some analysis later. Due to the particularity of the image, the pixels of the plain image are unevenly distributed, which makes the image easy to be corrected when subjected to statistically analysis attacks. The histogram can clearly show the distribution of image pixel values. On the left is the pixel value distribution of the plain image. The other is the pixel value distribution map of the cipher image. The pixel value distribution of the plain image is not uniform, but the pixel value distribution of the cipher image is uniform. Generally speaking, plain images have strong correlations in 4 directions: horizontal, vertical, positive, diagonal, and anti-diagonal, while cipher images have weak correlations in all directions. We select 5,000 pixels in Lina image, Baboon image, and the Pepper image, respectively, and calculate the pixel correlation coefficient R on 4 directions. The closer R is to 1, the higher the correlation between pixels. experimental results shows that the correlation of plane images is very high, but the correlation between adjacent pixels of the cipher image has been reduced to almost non-existent during the encryption process. In image encryption, there are often cases where the difference between two images cannot be observed by the naked eye. The two values MPCR and UACR are generally used to quantify the difference between images. Comparing where the values of the pixels at the same position of two images are the same. The ratio of the number of different pixels to all the pixels is the value of NPCR. NPCR measures the number of different values of pixels in two random images, but doesn't show the degree of difference in the values of pixels in the two images. So UACI is introduced to supplement. It describes the average value of the difference between the values of all pixel points in the same position of two images to be compared, and the ratio of the maximum difference value. Case-sensitive analysis refers to difference analysis of the cipher image obtained by encrypting the same plane image with two keys with little difference. To increase the size of an initial value by 10 to the minus 15th power to generate a new set of Celtic sequences. Encrypt the same plane image through two Celtic sequences respectively, analyzing the difference between the two cipher images obtained, and calculate the value of NPCR and UACI. Key sensitivity analysis refer to the difference analysis of the cipher image obtained by encrypting the same plain text with two keys with little difference. The results of the test and the comparisons are shown in the table. As can be seen from the table, the key sensitivity of the encryption algorithm is very close to the expectation. The performance on Baboon and Pepper are also better than the algorithms in reference 1 and reference 2. Next is plain text sensitivity. It refers to the difference between the contrasting cipher images when two images with very little difference are encrypted with the same key. If the difference between the two images is large, the plain text sensitivity of the algorithm is high. Otherwise, the plain text sensitivity is poor. Therefore, change the value of a random pixel point and analyze the difference of the cipher image after encryption respectively. The table below is the NPCR and UACI values of the images. It can be concluded from the table that the algorithm has better plain text sensitivity. Noise is manifested as irrelevant and abrupt pixels in the image, and the noise generated by the different methods is also different. The figure below shows the noise in the simulated channel and the described image after adding 4 cans of noise to the Lena cipher image. They are Poisson noise with variance 0.01, multiplicative noise with variance 0.04 and 0.04, Gaussian noise with variance 0.01, and salt and pepper noise with variance 0.1. It can be seen from the 4 images that after adding different degrees of noise, there is still a good decryption effect, even if there are errors in the values of some pixel points. The approximate image can still be seen. It shows that the encryption algorithm has a certain anti-interference ability in the face of noise attack and can restore the original image better in the face of interference, which provides a certain reliability guarantee for transmission in the channel. When transmitting in the channel, it will not only face noise attacks, but also sometimes part of the image will be lost. At this time, the encryption algorithm needs to decrypt the part of the cipher image that has been transmitted to obtain a clear, plain image as much as possible. Figure shows the cipher images and the described images after 1/8 cutting, 1/4 cutting, and half cutting of the Lena cipher image respectively. It can be seen from the figure that as the cutout part becomes larger, the decrypted image is distorted to a certain extent. Although the described image is not clear enough, the basic outline of the image can still be seen. Therefore, the algorithm proposed can still give a more complete image even if there is data loss. It can cope well with the need for real-time transmission. The information entropy was drawn and summarized by Shenyang in 1948 from the concept of thermal entropy in thermodynamics, which refers to the uncertainty of information and the level of information value. The information entropy of low information degree will be high. In the paper, the theoretical value of information entropy is 8. Table shows the information entropy of the plain images of Lena, baboon, and pepper and their separate images. It can be seen from the table that the information entropy of the Lena cipher image is equal to that in reference 1, and the other 2 images are slightly higher than those in reference 1. Meanwhile, the 3 information entropies are much higher than those in reference 2. Therefore, the encryption effect of the algorithm in the paper is better. Showing this PowerPoint are the 2 references previously used for comparison. Through the analysis of the chaotic system and the actual encryption effect of the algorithm, it can be considered that the encryption performance of the algorithm proposed in the paper is better. It can effectively encrypt the image to achieve the function of confidential communication. The above is all the sharing content of my paper. Thanks for watching.